Okay, so a three-phase balanced load, and it's a star. So, if you're looking at what that is a balanced star, and it's a 4-wire star. So you can tell it's a 4-wire star because you've obviously got your 1, 2, 3, 4. So you get your 3 colours. So that R, that's for red, the Y is for yellow, the B is for blue, and that one there, that's for the neutral current. Balanced means that these 3 impedances are the same value. So for balanced, all impedances are the same. And for your 4-wire, you've got your 3 lines, red, yellow, blue, and a neutral. So balanced, all impedances are the same, and then 4-wire gives you your 3 lines plus your neutral. So what you really talk about when you're looking at these is you talk about, well, the terminology, let's have a wee look. So you talk about line currents, phase currents, line voltages, and phase voltages. The line, if you like, is the part kind of outside of the star. This wee origin point here, that's the star point. This current at this point here, that's a line current, and as it turns down here, like past this point if you like, so if you look at like that as being the edges of the star, that's the line current, that's the phase current. So it's the phase current kind of inside the star if you like, and it's the line current outside. Then when you look at the voltages, the line voltages are the voltage between the lines. So like from here to here, that would be a line voltage. But between the star point and there, that would be a phase voltage. So that's really your terminology for it. Okay? Okay. We can go back to anything. Okay. So a balanced star, 4-wire, phase voltages. So phase voltages. So you've got your 3 phases. Do you mean a full circle? You've got 360 degrees. So these 3 phases are 120 degrees apart. They've got E there instead of V, so it doesn't make any difference, does it? So that's the voltage for the red phase, the yellow phase, and the blue phase, all being 120 degrees apart. And they're showing you here, if you take RO, so that's between the voltage between the red and the origin, which is kind of from this point here, if you like, to this point here, shown as being this arrow here. So that's really going from there to there. You're taking that as being your reference. So that's your reference phasor, has an angle of 0, shown to you there. Then you're looking at your YO, your yellow, as being either positively 240, so going round from this red round to here is 240, or negatively minus 120. One's the complement of the other. It doesn't make any difference. And your blue as being 120, or its complement, negative 240. Doesn't make any difference which one you do. But that gives you the phase relationship between the three. And this is kind of the bit that we're getting to. So if you want to get from a phase voltage to a line voltage, so remember the ones that go from the star point out to the extremity of the star, they're your phase voltages, and the ones that go from colour to colour, they're your line voltages. So if you want to get from a phase voltage to a line voltage, this is the method that you use here. So underneath here, this is the same phasor diagram that you had in the previous slide. So it's just the same as that. Yes, so they've just called that arrow. So that is the red phase voltage. So it's talking about something that goes from the star point out to that coloured line. So from there to there. And what they're trying to work out is how you get from a value going from there to there to a line voltage going between colours. So the one they're looking at going between colours is red, yellow. So they're looking at the voltage between here and here. So they're saying, how can you get from these voltages to this voltage? Now, if you just focus on that part, going from red to yellow, I'm going to get my highlighter to show you. Then the part you're interested in, going from red to yellow, is this part here. Now usually when you're looking at voltages and voltage drops, I'll take a wee aside. If you were looking at this and you were saying current would be coming from the positive in this direction, then your voltage drops would go against, wouldn't they? So if you're looking at a typical, looking at directions of currents and voltages, from everything we've done so far, you would always kind of say, well, the current comes out the positive side, there's the direction of the current with that arrow, and the voltage drops go against that. And then to get that total voltage, you would say that Vs is V1 plus V2. That would be normal, wouldn't it? So comparing this to this, so you've got your current coming in here, this one going against it. That's exactly as you'd expect there. But then you've got this one going with it. So this one, if you like, is the wrong way round. So when you're looking at getting the voltage between red and yellow, then starting at the red side, you've got arrow which is going the correct way, so you'd expect it to be like that. That's where that value comes from. But then instead of being plus, it's minus, because this arrow is going against. Do you see? So you would take this as being that, take away that. And that's shown to you as phasors as well there. And then you should also be able to do this by calculation. Now your calculation starts off based on this. So based on this statement here, which we've got from looking at this current path. So to get V red yellow, it's VRO minus VYO. And then you take their values for these two from these phase relationships here. So your VRO, that's your one that's got an angle of 0. So that's your V phase at an angle of 0. And then your VYO has got your angle of 240, your angle of minus 120. That's that there. Then you take out V phase as being common. Then make it 1 at an angle of that, minus 1 at an angle of minus 240. Convert it into rectangular. Then sort it all out until eventually you get V phase as that. And then that number, that 1.732, that's the same as root 3. And that gets you the angle. So it's a proof. So in that way, you can also work out this and this. And that is the first thing I'd like you to do. Okay? So I'd like you to copy down that statement, if you like. So that's the start and that's the end. And that statement. So you'll probably need a bit of page for each. So I'd maybe copy one down at the top of one page, one down at the top of another page. And then once you've got that, I want you to use a combination of looking at this diagram and looking at these three formulas to do these two proofs. I'll move that up, see if I can move that up so you can see that as well. Probably not. I'll chop it up. That, if you like, is all the information that you need. So if you're starting in this one, your first line will just say exactly that. So this is the first line of your proof. Then from that, you're going to have a wee look at your table here and go, right, yellow. That's V phase at an angle of 120, sorry, an angle of 240, minus VBO, that's B phase at an angle of 120. So that's kind of how you start. I'll pause this.